All right, welcome back. Sorry about that short delay. I had some issues on the computer. But I'm Captain Paul Weskelnies. I am the one and only mechanical instructor. I sit right next to Captain Austin, and we talk about energy, electricity, all the fun stuff that we want to try to solve the world's problems, or at least the Air Force's problems. But we're going to be going over energy optimization, the last part of 10-200-02. So we'll be talking about energy optimization. We've already hit on it in a few places. The last lesson talked about energy optimization, and we'll dive into it a little bit more. But I have you for 2 hours, and we're going to be able to talk about energy optimization strategies and then energy modeling. So this is what we're going to be going over. We're going to know how energy utilization impacts facility design for the United States Air Force. So we'll go over a quick overview, since we haven't hit on this yet, on how we use the energy, and then comprehend some strategies on how we can actually incorporate this into our design. So here's a quick overview. We're going to talk about resources, policy, and then strategies. Now, let's talk about the world. We have here a graph of the Human Development Index, HDI. This is devised on a bunch of different factors: education, quality of life, a bunch of different things, to say where do the countries rate on development index. And then we have electricity consumption down over here on how much do they use per capita. So how much energy does each person use? And we can see over here, we have India, we have China, and then we have, all the way over here, we have us. India and China are significantly low. They are running at about 2 million or 2,000 kilowatt hours per person per year. And they are at about 8.5 or 7.5 for China. For the United States, we are at about a Human Development Index of 9.5. So the question is, if we look at this for per capita, this is the trending of India, China, and ourselves. We are actually decreasing per person through energy conservation, but India and China, they're increasing. So the question I have for you is, what happens when China and India decide they want the same standard of living as us? It's kind of a big question. They have a lot of people. Compared to them, we have very few people. We're talking about a third of the world, third to a half of the world in population, and they are going to increase how much energy they use to try to meet our standard of living. It's going to be huge how much energy they want to use. So energy is going to be a big deal, and this could define our future conflicts. So how do we use energy in the US? Well, we have industry, transportation, and buildings. And buildings is broken down between residential and commercial. So the point that I want you to see on here is focus on the commercial down over here. We have at the very bottom, all the way over here, other. Then we have lighting. This is a bit of an old study, so lighting, I would estimate, is going to go down. Why? LEDs. We're using compact fluorescence, and we started at incandescent light bulbs, extremely inefficient light bulbs. So that could go down, but it's still going to be a large portion. Then up next, we have down over here, heating, cooling, water heat, ventilation, equipment, computers, cooking. Refrigeration, you're probably thinking, I don't have that many refrigerators. Does that really consume that much? Well, this is across industry. So this could also include supermarkets. Supermarkets have a huge refrigeration load. In fact, that ends up being 50% of their consumption. So we don't have to concern ourselves with that in the Air Force. But you might. We have commissaries, but for most of our buildings, that's not so important. So let's look at then, where is this energy coming from? So remember that last slide. Remember this, where we have this: lighting, heating, cooling. And then where is this energy coming from? So we have coal, natural gas, our largest energy producing means. And then over here, we have commercial, residential. All those uses we saw on the last side, but most of our energy is being lost to conversion losses. So if we're losing all of this energy to conversion, the system is not inefficient or is not efficient. We will have to find ways to better use our energy so we don't have to use conversion losses. But this brings in site versus source energy. If we're looking at the whole process to get you 1 kilojoule or 1 kilowatt hour of energy, we start all the way over here where we have to pull the resource out of the ground. We pull it out of the ground, we send it over here to a plant where we have to do our first conversion. We burn it. We burn the heck out of it. And then we convert it over to water, steam, energy, harvest energy out of that again, and then we send it out through distribution to your building. This whole process, and then we use it over here. This whole process is the life cycle of your energy, and this is what we call source energy. What you measure on your utility bill and what you use when we're talking about energy optimization is site energy. Site energy is really just from the meter in. What does your building see? So if we're talking about site versus source energy, what are some things, if we were to reduce the amount of energy we use at our site, we will reduce our source energy by 2/3. The factor that we say is source energy is about 3 times greater than your site energy. So we save a whole lot of energy over this. But in reality, we really only care about site energy. The rest of it is caring about the planet, which some of us like to do, but us in the Air Force, we just care about saving energy at our location. So if we want to save this energy, we may have to use on-site renewable energy. So here's a nice little graph that sums up where our resources. So we have over here, map of the US. And like Captain Tomaszewski, I really just wanted to have this map here so I can point over here at the different regions. So in the east, we have a lot of cloud cover. So we don't have much for energy from photovoltaics, from solar. The sun doesn't shine as much. It does not reach the point where we can use it. Whereas over here in the west, we have all sorts of sun. Where my home, sunny Colorado, man, miss that place. But in Colorado, we have a lot of opportunity to use PV. Another type of renewable is concentrating solar thermal. Very specific. This is where they put up that farm of mirrors that reflect it up onto a big tower. They heat a big mass of either molten salt, water, and that runs for a while, but it needs to be kept going. It takes a lot of startup energy, and then you have to maintain it. But it's really only viable in Arizona, California, in these southern parts, Southwest. Then we have wind. So if you didn't meet those other places, well, maybe your wind will work. So we have on the coastline, over here, we have on our coastline wind, that's possible. We have up over here in the Great Lakes, we can put wind offshore. And then across the middle, that whole area has a lot of wind. Biomass is another solution. You can harvest it locally. Excuse me. But where green things grow. And now geothermal. Very rare. I personally love geothermal, but we can't use it everywhere. A lot of places still in the West can use it, but over here on the east, mostly for heating, cooling purposes. Excuse me. Then we have hydropower. You have to have water. You have to have dams. You have to have rivers. So there's very limited on what we can do. And then tidal. Lastly, tidal. There we go. Wave and tidal. On the coast. So the West, well, the West is looking pretty good. They have all sorts of resources over here that they can use to generate electricity. This is a theoretical potential of how much energy is available. Sorry. I'm going to step off camera while you look at that. But this is how much they guess we could possibly use if we were to, say, line the whole area with, if we were to line the whole area with solar panels. Take a drink of water. So Alaska doesn't burn coal for energy. Thanks, Captain Tomaszewski. So Alaska doesn't burn coal for energy. What do you use for energy out there then? If you wouldn't mind putting that on there. Hydro and gas. Okay, so natural gas, if we, going back way a bit, natural gas has passed coal as the largest energy source in the US. So coal is diminishing right now, but natural gas is definitely increasing. The advantages to a natural gas is it's a lot better for distribution. So we have mixed coal at Eielson, coal, natural gas. Take your pick. Different resources are available. They don't use natural gas on the east as much because they don't have availability. They still burn coal. So let's take a step back. We're looking at the world, or we're looking at the US, and where do we use our energy in the DoD? Well, we'll take a look at this chart, and within the US, we have 99% of energy is used outside of the DoD. We control about much energy across the grid. But within the federal government, we'll take back even there, the DoD uses 80% of the energy for the federal government. But then we take it into the DoD, and the Air Force, well, we use 48% of that ourselves. And let's step back even more. Of all that, we as civil engineers, we only care about 16% of the energy. 81% of the energy goes out of the tailpipes of aircraft. But 16%, like, so why do we care about 16%? Well, 16% is still a big deal. So that's 8% of the budget in 2011 of our energy costs, $9 billion. Facilities energy, talking about $150 million. That could be, say, an F-22 or a good portion of an F-22, or that project that you really want on your base that you know you need. So it's a big deal. Oh wait, that's just the water. Take that back. I got more stats for you. So our Air Force facility usage. In FY17, this is our distribution of energy use. We have electricity, 52% of it. Natural gas, as we said, natural gas is getting much bigger, as I can figure out how to point right there, is 34%. And then we have coal, where we have a coal plant here at Wright-Patterson. Renewable electricity, only 1% is renewable electricity. But the cost to this, well, electricity is much greater than 50% of our energy usage. And this is roughly $1 billion of energy that we use every year. That is some big money. I haven't quite made my first $1 billion yet, and I'll probably die never making it. So it's a lot of money. I'm not going to have Amazon stock anytime soon, or new Amazon.com. They already took it. But so we've started saving energy. $1 billion. We can save energy. Well, if we look at our usage, we have decreased since '94, 44% of our energy. We've roughly cut our energy consumption in half. However, our utility costs have, well, go over to this slide first. Our cost per 1,000 or tera-BTU increased 94%, nearly doubled. So where does this shake out? It shakes out that our utility costs have increased about 8% since '94. So what this breaks down into is our consumption avoided roughly another $1 billion of energy costs. If we did nothing, we would have to pay $2 billion instead of $1 billion every year for energy costs. So this is a big deal. We still have places to go, and we're still trending downward. So they came out with the U.S. Energy Flight Plan. So our Air Force's energy vision: enhance mission assurance through energy assurance. Now, I mentioned earlier, I love renewable energies. We get to save the world. I'm from Boulder, Colorado, so I am part hippie. I want to save the world. I want to conserve. But I'm also part of the Air Force. So I want to make sure that we can take the fight to the enemy. We can put bombs on target. We can do what we do best. So not really a good hippie, but I love this stuff. So we want to have this energy available to be able to do what we do best. So energy assurance. They came up with our energy goals: improve resiliency, optimize demand, assure supply. And how are we going to do it? Well, ensure an energy-aware culture, identify innovative approaches, installation plans, technological advances. And because you guys are here, you are learning about innovative advances. We're focusing on this then: mission assurance, energy assurance. We want to, through optimizing demand. And through this lesson, you're learning about innovative approaches, technological improvements, and also the requirements on why we have to do it. Even if you didn't want to do it, we still have to do it. We're told to do it. But mission assurance, that is the goal of energy. If we can save energy in one building, we can use that energy in other places. They also came out with a fancy chart saying that we want to have projects that are green, are cleaner, that save money, and that improve resiliency. 3 goals. And then they said, if you can make all of those, that's the sweet spot. And then they said, well, maybe not. Let's do energy resiliency plus 1. So energy resiliency plus cleaner, or saves money. And right now they're just saying, we want to improve resiliency. You're like, what is resiliency? I don't even know what resiliency is. It's up there. It's a very big topic. But what we can do right now is to improve our demand. And that's by building better buildings. So here's all the guidelines that we have come out. We went over them. I know Ms. Shaw went over and covered these. Energy awareness and education would be MEROV usage. Not sure what you say by MEROV usage. Type that in, but I'll keep pressing on. Improve. Gotcha. Yeah, improve usage. Exactly. If we can go out there and tell people the turn off the light campaign, use your stuff better. Yeah, there's a lot of strategies out there. I was the energy manager at Kunsan. We had a 5K to try to bring awareness to this. But as long as people can start showing this, a great thing is show them their energy bill. Let them see what it is. But we'll go through all these. We're not going to talk about all these. These are all the guidelines that we've had come out. And then they came out with the UFC. And then they updated the UFC. So this is where I am pulling all of our stuff from. So UFC 10-200-02, High Performance and Sustainable Buildings. And we've probably hit you over the head with this UFC the whole time, and I am going to continue it. But this is what it says for optimizing energy. We're focusing on commercial buildings. There is guidelines for residential, but those basically say follow a different standard, but we'll focus on the commercial buildings. So meet the requirements of ASHRAE 90.1. 30% energy consumption from the ASHRAE 90.1 baseline. And if not possible, highest energy efficient that's life cycle cost effective. So this is ASHRAE 90.1. This is probably the thickest standard that I have. And it has all of these requirements listed out. So there are things in here that are required for you to do, and a lot of energy efficiency things that we need to do in here. But the 90.1 baseline, we'll talk about that in a moment. is a building that is prescribed by here saying you should be meeting these requirements at your given location. And that's where you start from. It's a baseline building, and it's not necessarily a real building. You're going to plug in values for walls that are in there, and you'd have to find the materials that match this to try to validate what this building would look like in reality. But a lot of energy modeling software goes out there and says, okay, what is the U value for the window? So on and so forth. So renovations, talked about them, existing buildings in the last one. So pick one, reduce 30% FY 2003 baseline, 30%, to 20% below 2015 energy use baseline, and then 20% below modeled ASHRAE 90.1. Now those first two are really only feasible if you have data for it. Well, the good thing is the UFC says you should install utility meters on each building for each utility. You have to have this data. If we want to optimize energy, you have to have this data. So it was a little shocked. I didn't quite read that it was an additional requirement for metering. But for a lot of buildings, it's only if they are going to be your top consumers, they require a meter. But if you want to improve things, you need to know where you're starting. So metering ends up being important. If you've identified a building that you are going to do a renovation on, install that meter on there a year in advance so you can get a full year's worth of data so you can make informed decisions. So if you take the 2003 baseline from your metadata, you can build it. And then 20% below modeled ASHRAE 90.1 baseline. You'll have to model it. You'll have to put it into software to figure out what is the energy consumption. And that's the same with the new building. Standby power devices, no more than 1 watt in standby mode. On-site renewable energy, where life cycle cost effective. And then solar heating, 30% of your annual domestic hot water unless not life cycle cost effective. Now we got a lot of people up in Alaska, so you're probably like, yeah, right, solar water heating. That sounds good. Maybe in the summer, we get a lot of sunlight in the summer up in Alaska, I'm assuming. But it's also cold, so maybe not so effective. And then in the winter, no way. So this all depends on your location. If we go back here, here's our US energy consumption. Told you to remember this, but I don't have a great memory, so we'll show it again. We have over here our lights, heating, cooling. So this is where we're going to focus the bulk of our energy optimization strategies. All right, before we go on, I'm going to drink some water. If you have any questions up to this point, please shout out or type them on the Connect. All right, no questions? All right, now that we got the policy out of the way. So what is the ASHRAE 90.1 building? So ASHRAE 90.1, it has multiple methods. It's completed through a prescriptive method outlined in 90.1. Baseline assemblies in your energy modeling software. So this is a screenshot that you can see it from TrainTrace. Down over here, you can see these different buildings per 90.1. 2007. So it changes. Values aren't necessarily linked to materials. You can see all these materials listed in here, but then you have these, which just plugs in the values in the table. And then they're climate zone dependent. So you can see down here, zone 1 and 2, 3, 4, and 8. So each zone will have different requirements. So where do we start? Where do we start in optimizing the building? Well, we can improve our envelope loads. We can then minimize building performance loads, and then minimize connected internal loads. For the Air Force, when we're talking about life cycle effectiveness, we may not include these minimized connected internal loads because we have equipment. We have a lot of equipment and they are mission dependent. So we have to use those regardless. So we may not include those in the life cycle cost analysis. But envelope loads, building performance loads, HVAC equipment, what do we have to put in here for the building itself? So let's talk about how heat enters the building. So if most of our energy is from heating and cooling loads and lighting, we can only do a few things, but we start employing daylighting, we're going to start affecting our heat gain. So a lot of our energy comes from the sun. So the sun over here, it shoots out radiation, and some of it gets blocked by this cloud. It gets blocked by the cloud, and we now call this diffuse radiation, and then it hits your building. We also have direct radiation, so comes right over, and then it hits your building, and then it may hit your window. When it hits your window, it goes into your building. It comes in, hits your floor, enters as a heat gain. We then have light that reflects off the whole rest of the world around you, and that's reflected radiation. You also have the outside environment. So you have out here what we call TO, or outside temperature, which is going to conduct through your building walls. So your envelope resistant value will then determine how much of that gets through or how fast it gets through. And it comes in to your building, and then it warms your inside surface. Now this radiation also warms your inside surface. When it warms your inside surface, it doesn't necessarily become heat. You don't feel the surface temperature of your walls. You feel the temperature of your air. So it then convects in off of your building, off your surfaces. You have over here, you have your lighting. They radiate as well. And then they also have convection. You put your hand close to a light bulb, it's going to feel warm. You then have people like myself standing over here. And we radiate as well. Everything that has a temperature radiates. If you don't have a temperature, well, you still will probably radiate. You're going to absorb energy. But everything radiates. And then it convects off. But also, I'm breathing. And because I'm breathing, I am now exhaling water into the air and hot air into the air. Lots of hot air, especially right now. But over here, we then have equipment. And that equipment, it's a black box. It could be your server room. It could be the lights of a studio. It could be a lot of things. Exactly. Install better glazing with reflective coatings, plant trees to help shade. Man, you are beating me on this lecture. So you're reading ahead on the slides, or you already know this. Either way, we're covering it. But yeah, exactly that. Those are things that you will have to do to optimize your building. But you'll have to do this based on your site. So talking about glazing and reflective coatings. So let's first start off by minimizing your envelope load. Maximize your orientation. I know Captain Tomaszewski was talking about how do you site your building? How are you going to orient it? That will affect how much energy your building uses. If you have an existing building, well, sorry, you can't just pick it up and rotate it. Take that back. I've seen it done, but most of our buildings are pretty big. I've seen that done to houses where you just pick them up off the ground for flood purposes. That'd be a very big cost to lift it up and rotate it around. Also, we don't have space. But I would love to see it done, but we don't have money. Sky-side obstructions. Say that really, really fast. So plant trees. Help shade awnings will deflect sun. Exactly. I couldn't have put it any better than Daniel. On existing buildings, raise topography and plant trees. Man, you're spot on. So exactly. Site sky obstructions, your trees, that will all deflect radiation, block it from the sun. Optimize glass R values and transmittance. Optimize roof R value, absorptivity and reflectivity. There's been a big push to paint your roofs white. At Holloman, we were painting our roofs white. And what does that do? Well, it increases the reflectivity and decreases the absorptivity of the roof. Just by that, you can save significant energy. And one of the biggest loads, I went through and did a study on AFIT for another lesson, is heat. And I was looking at two different materials on the west side of the building and how fast they were heating up. The dark one was heating up faster than the light one. We all kind of know that, but we don't really think about that all the time with our buildings. Simple things you can do. And then optimize wall and floor thermal performance, thermal mass and resistance. I'll talk about each of these. So if we look at sun and building orientation, so the sun rises in the east and sets in the west, at least for today, and hopefully for tomorrow. But that's how it moves. So when we're talking in the summer, or both summer and winter, in the morning, the eastern face will get extremely hot. Just on AFIT, I measured surface temperatures of about 130 degrees in about July. Green roof vegetation. Yes, it's the difficulty with green roof vegetation is it's hard to model at this point. But a lot of people are using it. And it's a great idea. Innovative approaches. So we talk about in the east, so hits that 130 degrees surface temperature. That will move into your building. Then as it rises, the sun will take an arc over, they'll go over your building, increase your roof's temperature, and then increase your southern face. Your roof will then reach, I measured again, about 130 degrees. And then on the west, when it starts to set, about 5, 6 o'clock, you'll hit your peak energy load when your western face takes the brunt of the sun again. Once again, reaching about 130. I didn't actually measure that. I went home. I did not stay here for the sake of science. I apologize. So in the summer, when it does this is going to be very high, a very high arc. And then in the winter, it's going to be a low arc. So that's going to heat your southern face much more. But that's a good thing in the winter, especially if you're in a place, say Ohio, where we have really cold winters. But in the summer, not as good. But that's okay. We can put in overhangs. And also in the winter, we can have glass to let the sun in. So this diagram will show you how the sun will change with the seasons, the movements across. Wind. If you're in a windy place, you may need to consider this. They discovered is if you orient the long axis towards the prevailing winds, you can end up maximizing a cooling effect. So if it's really hot, you can cool your building. So that's with it. So as you can see over here, is the long side of this, is running parallel with the prevailing winds. You get a cooling effect. If you rotate it 90 degrees, you will then reduce the cooling effect. Then we talk about raising the elevation. Well, if we have a higher elevation, we can block the sun. Natural vegetation also looks good. If you're in, once again, if you're in a colder environment, you may want to allow the sun to get in though, more often. So you're very climate dependent on what you are going to do. So here's an example, pretty picture, of natural shading to cut the reflected solar load. You can see this building face here is still being lit up, but you're not getting reflective loads in. So you're still getting some daylighting in, but you've now cut down your loads on your building. And this, I would assume, is your southern face. Now for your solar shading example, you can see this overhang right here will protect your windows from the sun during the summer. When the sun is high in the sky, the sun will not shine into your windows. But when it's lower in the winter, you will allow that sun in decreasing your heating load. But when it's high, you'll then block it, decreasing your cooling load. Vertical shading, help reflect it on your southern face for rising sun and setting sun. The sun is very intense and very direct at that point. You may think, oh, it looks so nice, peaceful, and serene. But the sun is just as intense then as it is midday. We just don't feel it. because the temperature hasn't increased. Thermal mass. Now, thermal mass, this ends up being what my thesis was on. So I did a lot of energy modeling, and my thesis was to say, hey, if we have a building, can we use the thermal mass to decrease our cooling loads, decrease our energy bills? And my conclusion with this was, because I used a lightweight building, no, I couldn't. So I felt like a failure, but they still gave me the degree. I guess it's like a finisher's medal, but I still got it. Learned a lot about things. But our cooling loads start slightly later and lower. So if you look at this chart right here, the blue, the dark blue, this is a lightweight building. The building will change very quickly with the temperature, outside temperature. So you can see right here is the temperature increases as the sun goes up. Outside temperature increases and the building goes right up there with it on your cooling load. And then at night, it cools down just as fast. But if we have thermal mass, well, at night, that thermal mass is going to get colder, and it's going to continue to get colder. So we look over here, and it doesn't decrease as much, following the purple line or the pink line. It decreases slower, but when it's here, now they're even. So when the temperature starts increasing, and it gets warmer than your thermal mass, well, that thermal mass is now going to absorb some of that energy rather than just passing it straight into your space. So it's going to absorb it, delaying it, and then in doing so, it'll decrease your peak energy load. And then you get down over here, but then the sun goes down, temperatures decrease, and it'll stay warmer longer, but that's okay. At 2100 hours, hopefully, none of you have to be in your office. So it's a plus. You don't need to condition the space at that point, and everybody's happier. So then other strategies you can consider. Minimize building performance load effects. So your HVAC system. So you've gone through and you've optimized your envelope. You've done it based on your location. So I like thermal mass. I really love thermal mass. You can do a lot with it. Denver, Colorado, great place for thermal mass. You have high temperature swings. You have, at night, 30-degree drop in temperature. Great place to store energy. Florida, not so much. Ohio, not so much. The temperature differences don't work. So you've gone through and you've said, this works here, this doesn't work here. Sorry about that. Our HVAC systems, so we can then go in, how are we going to meet that load? Well, we have to use HVAC systems. There are ways you could do called passive buildings, but those are difficult, and you have to really study them for them to work. But we'll have to slap an HVAC system on there. So we can improve that. We can look at daylighting, passive solar. So instead of putting PV on there, how can you use the solar to counter things off, to counter energy, especially in the winter? And then green roof systems, as mentioned. But energy modeling is not well established. So here's some efficiency measures that you can do regarding your HVAC system. So you can install an economizer on here. Variable systems, air-water control, single zone controls, reset schedules, energy recovery, duct leaking. So here's an example of your economizer. Your economizer works by saying, hey, it's cold outside, yet we still need to cool our space. So if it's cold, let's bring in cold air and just exhaust all that hot air. It's hotter than the outdoor air. So a typical system, we would return that air and then recool it again and bring in as minimal outside air as possible, which is smart during parts of the day. But if it's, say, in the morning, we can save that energy by just exhausting it and bringing in possibly 60-degree air. We may not have to even cool it. And this is one of the things I did in my thesis was, how is this economizer going to work? And yes, you save energy just by using economizer. Variable system. Why do we want to just cool the system the whole time at the same rate? It's going to change. Well, let's adjust our airflow. Let's adjust our water flow and we can better meet the system. Your house, probably not a variable system. Turns on, then it turns off. Variable is what the variable system, variable air is what we use in the Air Force in most cases. You can put in a reset schedule. I skipped the zone control. By maximizing your zone control, so if you have more zones and decreasing, you can then control each zone more specifically. If you don't have a load in one of your zones, why cool it? Well, if it's connected, well, now you're dumping cold air into an unoccupied room. So if you can better zone your building, putting thermostats in those locations, you'll save energy. Now, reset schedule. Most places we use this in the Air Force. This is actually a picture from my Ecobee, because I am a geek like this at home. I love putting all this home automation stuff. And so this is our Ecobee. This is a reverse reset schedule. So if we look over here, we have during the night. I like it cold, so I decrease the temperature. Then in the morning, I don't need to sleep when it says cold, so it increases the temperature. And I allow my temperature to slowly rise up in the morning to that set point. I'm not using any cooling at that point. Then, during the day, when I'm not there, why bother cooling it? So I let it creep back up. Then, over here, let's go over here. Trying to figure out where to stand on here. Right about here, the Ecobee kicks on. I think it's using some kind of predictive control, so it's nice and cool and meets my set point when I arrive back at home at night. So opposite reset schedule. If you were to do this for your office building, it would be opposite. At night, you'll decrease it to say 80 degrees because nobody is in here. But you will still have to use temperature control, mainly for humidity. You can't get it too hot, and then you have to ramp up early in the morning. Simple ways with controls. If you have a control system on your building, you could probably do that already. And your EMCS shop is probably already doing that. If you're more aggressive on it, you could possibly save more energy. Energy recovery. Heat pipes. Well, this isn't a heat pipe. This is an air-to-air exchanger where we have hot air coming in from the outside. It crosses this exchanger and goes into your building. But we've just cooled down our building. So we are going to pull cooler air from our zones, conditioned air, but not, it's still warmer than your zone. And we're going to pass it across here, and then we're going to exhaust it from the building. And this will provide us with energy savings because we have just recovered some of that energy that we have already spent and pre-cooled the outside air. Now there's other technologies such as heat pipes and enthalpy wheels to also help with humidity control. And then duct leak testing. So I see the comment on there, better circulation will provide better cooling without air conditioning. Okay, that's true. I saw better circulation, so I'm going to touch on that point. So if you have duct leak testing, making sure all the air is going where it's supposed to. If you have in your ceiling, your conditioning area above the ceiling, you're just wasting air. It's just like leaving it's like a drip on your faucet. That's just water you're not using. So if you can get it all going to where you need it to be, better. Better circulation will provide better cooling without air conditioning, as said there. Yes, you can do that, especially if you have different zones, like one zone gets really, really hot. Well, if you can pull cooler air from another zone that's just sitting there, there's a lot of ways you can do this. It gets very complicated very, very fast on here. That's why HVAC's fun. If it was easy, everybody would do it. But there's a lot of options that you'll have to look at on how you're going to make your HVAC decisions. So what we have here is a UFAD system, underfloor air distribution. And you can see here a raised floor with ducting underneath it. But what this does is the design premise to this is we are going to cool the air from the ground all the way to about here, or maybe a little bit higher. I think it's it's 8 foot. Because most people are not 8 foot tall, we don't need to cool this area up here. Nobody's running around saying, I need to breathe up there, or I am sweating because it's really hot up here. So if we can cool up to 8 foot, we will now reduce our zone, especially in large office buildings where you may possibly have higher ceilings. And we'll show some of those when we're talking about some of these design strategies. So we then pump air underneath the floor, and we pump it up into the building, and you just cool that zone. It's very simple, and cool air will actually, cool air stays low. So we only cool that area, and then the hot air will exhaust to the top. Very modular. You can see if they were to pressurize this whole area as a plenum space, it's very modular. If you have a change in your floor, you can just pick up one of these tiles, move it over here, and you have cooling over there. Or you can hog it and take these tiles and put them all underneath your desk, and now you're only cool. But that's okay. If you put one of these in, keep that to yourself. Natural ventilation and operable windows. So last summer, not this summer, but the last summer, I was working at NREL, and they had operable windows. So this works like an economizer, but directly for your spaces. So when it was cool outside, they would open, these windows would automatically open and automatically close when there was favorable conditions for natural ventilation. Or you just open the windows when you know it's cool outside. Of other strategies I've heard are they installed a NOTAM on everybody's computer, and they kind of made it a game. Hey, it's hot outside, close your windows, and it'd have a little alert up there, and you'd go close the windows. And you create a little game by saying, you save this much energy by opening and closing your windows. There's some fun things you can do with this, but with the Air Force, so it's not going to be fun, we'll just open them, close them, and you're kind of counting on people to understand them. Or install a fancy system like this. All right, lighting systems. So 26% of your energy before LEDs can be used in your lighting system. How do we fix that? Well, without replacing LEDs all around there, we have on here complex and less complex. So less complex, you tell people to turn off the lights. This sometimes works, but I don't know how many of you come back home from a vacation and say, hey, I just left my light on in my bedroom for the month I was gone. Great. I'm going to pay for that. So fallible. So we can go over to automated lighting systems. I heard Captain Austin talking about this. These work great. Somebody walks into the room, the lights turn on. We had these at Holloman, where we had these automatic light sensors, and my cubicle was in a place that was not seen by the lighting sensor. So it just told me about every 15 minutes I need to go up, stand up, and then turn on the light by triggering the sensor. But this works to save energy by not lighting a place where nobody is going to be here. Simple thing. We don't need to use the energy if we don't need to use the energy, so turn off the lights. And it'll do this for you. Take that human element out of it. Now we can get more complex on here, and we can talk about daylighting. I learned about daylighting as I was working on an awards package. I was taking CBTs on the Whole Building Design Guide, or FEMP CBTs, where they then went through and discussed daylighting. I had no idea how well this would work. But the idea is you can reflect light in with a light shelf, and it reflects up onto the ceiling and distributes through your ceiling reflection. Then, possibly in the winter, you want to let that sunlight in. So now that heats up your floor. Then, even later in this winter, you want to let more sunlight in, but you don't want it onto your occupant. So you'd have to block the light with some way. You'll have to block the light possibly with a desk or how you arrange it. So it gets complicated then. And then you integrate that with a daylighting sensor or a lighting control system. At NREL they had these, and they worked pretty good, except they could have worked better. They would turn on and off, and the lights would be suddenly very bright, and then the daylighting sensor would say, hey, you have plenty of light, and then they would turn off. But they'd turn off like that. So kind of got distracting. But in the end, you save energy. You take advantage of that energy from daylighting. And ASHRAE 90.1 has baseline lighting power densities. So as you're going through and you're figuring this out, you'll have to refer to the baseline power densities in ASHRAE 90.1. So daylight harvesting, this is complicated. We have daylight sensors, and thanks, Mike. We have daylight sensors that can take care of this. Oh, sorry about that. Got distracted. Daylight harvesting. So that ends up being the process of implementing this daylighting and all that we talked about on the last side. We have passive solar. Now this is going to end up being building your building to heat your building in the winter. As you can see over here, low winter sun and high summer sun. When we have the low winter sun, you let more light into your building, and this will increase your temperature. The high summer sun, once again, we block it. But you have to then design thanks, Mike. Sorry about that. My clicker died in the middle, and I didn't ask for help, but Mike is on top of it. We have great support staff over here. Really, really the best. Another option we can have on here, and it's shown down over here, is you heat up a wall inside your space. And by heating up the wall inside your space, you then bring energy into the building without bringing light into the building, possibly going against your daylighting strategies. So here's an example of maximizing your daylighting strategies. You can see about where my head is. I'll move it. We have over here lots of daylighting. Then you look at each of these rooms, they are segregated from the rest of that main hallway. So this hallway, you don't have to heat or cool as much, but this side now are your conditioned spaces. You separate these loads and you can save energy that way. This is the NREL facility. This is actually from in Pennsylvania, but this looks exactly like where I sat, where they're allowing daylighting to come in over from these windows. They hit the wall, which reflects down and onto all the occupants. Facility orientation, you want to orient it so you can optimize daylighting. Over here, can't get much daylighting, a lot of shade. Over here, you can. So how you play into how you orient your building will play into your daylighting strategy. And then optimizing your space. One is flexible, but two, if you can have an open space, you can better distribute daylighting through that space. Other energy strategies, well, reduce your plug loads, ventilation loads, and then how people operate in the building. If people can work better or with better strategies, one that I've heard is that let's just not have people come in to work on Fridays. If you work a 4-day work week, you don't have to cool that building for a day. Now, nobody will catch on to that. I would try to ask my boss for that, and he said no. But there's ways you can save energy that way. For your plug loads, talked about the Energy Star system program. A lot of these are describing your power draw, off-mode power draw. How do we decrease those standby losses? And then how efficiently do they run? But you could save roughly 20 to 30%. This is the NREL building, but I'm running long, so we'll skip that. So this is the Net Zero Energy building. They are very proud of it. The National Renewable Energy Laboratory. I sat somewhere over right about here. Had a window cubicle. But you can see they maximize their east-west orientation. They get a lot of daylighting in from the southern face and then minimize that east-west. In Colorado, I mean, you can imagine it has a very high sun. The sun will really heat up the building. Then they also slap PV all over it, photovoltaic cells. But this is a cross section. So you can see that top floor allows a lot of sun in from the north. Also, I think that's from the west. Well, they bring sun in from there. They have underfloor air distribution. They have radiant heating and cooling, which work great, and they're also very, very quiet, which is a bit unnerving because then you hear everything in the office. But then you have thermal mass. Once again, this is in Golden, Colorado. Thermal mass works very well with these high temperature swings. And then they have what they call the labyrinth down over here, which ends up being where they bring in air and they store cold air at night or hot air in the winter. So we just ran through energy optimization. There, we could spend a whole week on how do we save energy in your buildings, but I gave it to you in an hour or more. So these were our lesson objectives. Know how the Air Force uses energy, and then comprehend some strategies on how we are going to implement these and save the Air Force money. All right, with that, do we have any questions? Anything? Appreciate the comments in there. No one person's awake, but if you have any questions, feel free to let me know. Either hit me up, email, the whole world out there on this. With that, I'll give you a 10-minute break. All right, Mike, can you put them on a 10-minute break?